We're privileged to have you and listen to. We are happy to listen from you, sir. Over to you, sir.
Thank you. Can you see my slides?
Yes, sir. We are able to see your slides.
I'm not okay. So yes, okay. Thank you.
Yes, I'm able to see your slides. Yeah.
Thank you. And you can hear me, I guess. So let me also.
Yes, I'm able to hear you very well.
Cool.
We are able to hear you very well, sir. Yeah.
Good. Okay. Thank you. Thank you for inviting me, and thank you all for joining this meeting. As thanks for the introduction. New York University. What I'll do is I'll do it a couple of things. How much time do I have? About 35 minutes or so, because we started a little late. Should I still keep it to?
No, sir. You have 30. Sorry. You have 35 minutes, sir. We can have a 10 minutes question answer session also. So totally you have 45 minutes.
Okay, thank you. So what I'll do is split this talk into 2 or 3 pieces. The first piece will give a high-level overview of what we do at NYU Center for Cybersecurity. And then the second part is where I'll talk about the high-level approaches to hardware security, which is the emerging regime of hardware cybersecurity. So NYU CCS continues to impact the emerging world of IoT, wherein the basic trust in society is at stake. It does so in at least 3 ways. First, what we do is we build secure systems at scale, and we make sure that the systems are unhackable. We consider systems at the hardware level, at the software level, the firmware and embedded systems level, holistically, and deploy them at neighborhood, at city scale, and global scale. Second, we secured the important supply chains, such as the electronics, the software, the control systems, and the digital manufacturing. Finally, we fight cybercrime at a global scale, including financial cybercrimes and cybercrimes, for example, against children. Just to reiterate, cybersecurity at NYU is a global scale effort. CCS spans multiple schools, for example, School of Engineering, where I am, School of Arts and Sciences, the Law School, and the Business School, among others. CCS has a strong presence in the Middle East. CCS Abu Dhabi in NYU Abu Dhabi is our beachhead in that area. CCS Abu Dhabi, besides offering all the advantages of routine advantages of being able to do cybersecurity research, offers us to investigate the cultural perspective of these emerging cyber threats. Here is the core cybersecurity team at NYU. This team looks at cybersecurity from multiple angles in a holistic fashion, as I mentioned. We see it as an IT and as an IS, as a CS problem from the chip level, firmware level, embedded systems, all the way up to the networks and systems. We see it as a human psychology problem. We see it as a human rights problem. We see it as a risk and risk management problem. Of course, it is an economic risk problem. We've been addressing cybersecurity since roughly 1998-ish, before cybersecurity became important. For example, in the USA, we are an NSA Center of Excellence in cybersecurity research. Our faculty, about 20 or so, mentor about 80 PhD students and over a dozen researchers. Some of our current research areas span critical infrastructure security. For example, that was one of the talks that just preceded my presentation. including in the power grid cybersecurity, transportation, and digital manufacturing. We also have expertise or research in supply chain security, hardware, software, digital manufacturing, for example. We also look at security of AI, the most recent being security of what are called the large language models, backdoors in machine learning models, and all the way to deep fakes and so on. Finally, we also look at AI applications in security, securing the hardware, in securing the firmware, and in securing the software, and in securing the entire system. My colleagues serve on the technical program committees of leading cybersecurity conferences. So, for example, IEEE SNP, Usenix, CCS, NDSS, and so on. Our center has dedicated space in Brooklyn, New York, 10,000 square foot, and about 8,000 square feet of space in NYU Abu Dhabi. We offer, this is something probably of interest to you, we offer a dual degree program with IIT Kanpur. And we also are building a joint PhD program in cybersecurity between NYU New York and NYU Abu Dhabi. We collaborate and partner extensively with universities, the governments, and the NGOs and industry. Our research is funded by various organizations, including DARPA, ONR, and so on and so forth. We have raised over $40 million to conduct research over the past 66 years, rather. We've been addressing cybersecurity, as I said, for close to a little over 15 to 20 years. We are only a handful of institutions that have the trifecta of distinctions for excellence by the National Security Agency. As I mentioned, we are an NSA Center of Excellence in Cybersecurity Research. Besides, we are an NSA Center of Excellence in Information Assurance Research and in cyber ops. The excellence in cyber ops recognizes and celebrates NYU's rigorous, practical, hands-on approaches to cybersecurity. And cybersecurity, both in terms of offense and in terms of defense. And it pervades our curriculum, underpins our research, outreach, and capacity building, and of course, workforce development activities. We have strong federal agency ties, which include training students for the government service. We offer, for example, we also offer an MS in cybersecurity and an online program called Cyber Fellows in cybersecurity. And a joint with the NYU Law School, we offer the MS in Cyber Risk and Strategy. And we have also, we do what's called the Bridge to Cyber to help transition non-STEM students into the cybersecurity workforce. This is something that we are most passionate about. Besides, of course, research and education, outreach. NYU CCS has a 20-year strong outreach program. CISA, for some of you who may be aware, is the largest student-run cybersecurity event in the world. It is held simultaneously in North America, in Europe, in MENA, and in Asia out of IIT Kanpur. CCS has about thousands of participants. CISA has thousands of participants annually. It organizes numerous competitions. For example, CTF, we call it Embedded Security Challenge. I call it Capture the Chip, cyber policy competitions, and so on and so forth. If you go to the website cisa.io, you'll see the events for this year. We also organize one of the things we do is our classes that we teach use many of these challenges as examples and homeworks. These challenges and the outcomes of these challenges are also used by other institutions. We organize the Successful Women Leaders in Cybersecurity program. We have a Hacker in Residence program, and so on and so forth. Let me see where am I. Yeah. So coming back to the topic for my presentation, over the years, electronic hardware has become the core root of trust for all systems, from buildings to pets and everything in between. However, globalizing the electronic supply chain over the last 2 decades has introduced numerous security issues. And because of this, the electronic hardware root of trust is no longer trustworthy. The systems that use them are no longer trustworthy. What I'll do is I'll paint my vision of hardware cybersecurity and the implications on how integrated circuits and systems will be and should be designed, and more importantly, continuously validated. High-level synthesis, when I say high-level design approaches, I mean high-level synthesis, especially in the context of hardware. It's a design methodology that translates high-level specifications, for example, in C and C++ into gates, either as an FPGA or as an ASIC. HLS research started in early 1990s. However, it did not take off until very recently as a commercial product. The reason was it was not ready for prime time. Performance, power, and area metrics were not good enough. In those times, circa 1990, logic synthesis was sufficient and effective in managing the complexity of the designs. So fast forward 2010 or 2012 or so and beyond, designing at these higher abstraction levels has become a prerequisite to manage complexity. High-level synthesis at the same time has become competitive in terms of the PPA metrics. Besides, it offers at least 4 benefits. 1, it reduces the design time. 2, it manages design complexity. 3, it reduces verification effort. And finally, it enables hardware, software, co-design, and co-verification. Mentor Graphics, which is now Siemens Mentor, Cadence, Intel, Xilinx, and other companies offer HLS tools. Several of the top 20 semiconductor companies use high-level synthesis tools. The cumulative annual growth rate, CAGR, of gates per centimeter square is about 59%, roughly, according to this study by Semico. At the same time, the CAGR of design or designer productivity is only about 25%. And this has created a design productivity gap, as you can see here. By raising the abstraction to the high level C or C++, HLS or high-level synthesis allows bridging this gap, hopefully. It allows for early design exploration, and the applications typically used by HLS include data-dominated applications such as image processing, crypto, machine learning, video, vision, and so on and so forth. Video components in the Tegra X1 chip are designed or were designed using Catapult HLS from Mentor. NVIDIA 4K processing unit was designed with C-based HLS. Qualcomm designs parts of its Snapdragon processor using, again, Catapult HLS. Okay. Here is a related trend. IC and system designs are using third-party IPs. For example, while there were about 16 or so IP blocks in a typical phone at the 90 nanometer node, it is projected that there will be about 200 or so IP blocks at the 22 nanometer node. So the increasing number of accelerators has its benefits. Quick design time by trading off integration for actual design. Benefit from specialist focus on these individual accelerators and specialized cores. On the graph, you see the red line. It shows that by about this time or about in a couple of more years, about 95% of a design could be mostly integration of accelerators sourced from third-party vendors. On the other hand, these accelerators and the third-party IPs may compromise security of your system. Attackers in these third-party IP vendor companies may embed, for example, backdoors and insert Trojans in these accelerators. Now let's look at the blue line. It shows the cybersecurity investments, both actual in the historical sense and projected in a futuristic sense. Some of this will be to deal with these accelerators, some of which will be to use these accelerators for security. So here is a typical HLS design flow. I don't know if you can see it clearly, but the background is a little dark. Hopefully you can see it, but on the top left-hand side is a specification that is translated into an intermediate representation called the control data flow graph. That's shown in the middle. And this is what software compilers do as well. HLS leverages these state-of-the-art compilers, for example, GCC or LLVM. And then in the scheduling step, operations in the CDFG are mapped to clock cycles. Some of them may take a single cycle, others may take multiple cycles. One can get fast schedules that are resource intensive or slow schedules that are resource constrained. In the next binding step, right on the middle and top of that figure, the scheduled operations in a clock cycle, maybe let me see if I can. Yeah, this is right here. The scheduled operations in a clock cycle are bound to operators. For example, multiplication operations are bound or mapped to multipliers. Addition operations are bound or mapped to adders, and so on. Similarly, data transfers that span or that cross clock boundaries are bound to registers. Finally, you get a data path as shown below, right here, and a controller as shown there. The controller sends control signals to execute operations on the specific chosen operators. Since operators and registers are reused, you see multiplexers sitting in front of them. The select signals of the multiplexers in the data path are controlled by this controller. Let's see if I can. Cool. So let's look at a current application domain of crypto and more importantly, post-quantum crypto. Since quantum computers can break RSA and ECC that underlie public key crypto, and since quantum computers cannot break AES and SHA, which are the private key crypto and hashing, PQC asymmetric crypto replacements for RSA are being developed. So the US NIST, National Institute of Standards and Technology, is standardizing PQC algorithms. The process started roughly about 4 or 5 years ago. In round one, there were 82 submissions. In that round, they were mostly evaluated for security strength. For rounds 2 and beyond, that is round 2 and 3, implementation trade-offs were considered as well. As of a month or so ago, NIST announced these winners. And for those of you who are following this, Saga, one of the potential fourth round candidates for key encryption, key encapsulation has already been broken. It's called Psyche. So to manage this aggressive standardization schedule, we used high-level synthesis to study the implementation trade-offs. We started with the input C codes from NIST PQC round 2 submissions. We changed these C codes to make them HLS ready. And this requires a lot of effort anyway. Verified the changes using the known answer test that the submitters provided to the NIST. We used, at that point in time, Xilinx HLS to study these implementation level trade-offs in this tight time schedule. These codes are publicly available for both the C codes and the scripts for HLS are publicly available. While the designs might still not be as efficient, they're customizable and they're useful for design space, rapid early stage design space exploration. And that was, in some sense, informing the standardization process. So we've seen how HLS can be used to accelerate or used to design crypto. We started with C-based design and translated into ASICs and FPGAs. So now I'll talk a little bit about the security awareness of HLS. So let me consider or suggest using security as a design metric. Most hardware security research has focused on the gate level, the netlist level, and beyond. Obviously, at this stage, in these stages, one loses important semantic information and are left with structural information. So securing the right parts is hard. Security-aware HLS allows one to secure a design at the high level. So high-level or algorithm-level security secures or uses meaningful semantic information. For example, even a non-security conscious design engineer can easily identify or easily suggest artifacts to protect sensitive info at this high level. High-level synthesis and register transfer level, which is a step below, have sufficient semantic information, while gate and layout level have structural information mostly. So if we stop right away, these are going to be the takeaways, and I will spend time on these takeaways in the next 5-10 minutes before I close down. So what the key takeaways are: high level is a promising level to design accelerators, including security accelerators. High level is a promising level to build in or design in security. High-level synthesis can be used for a variety of security awareness tasks, such as Trojan detection, Trojan isolation, watermarking, and obfuscation. High-level synthesis can also be used for incorporating taint propagation in designs. Some of you may be aware of taint propagation in software, but you can bring that into hardware as well. It also has its drawbacks. High-level design can be, or HLS-generated designs can be reverse engineered. time permitting, I'll spend some time on this. For example, similarly, a black hat can use high-level synthesis to undermine designs, weaken crypto, drain battery, and so on. With those key takeaways, let's come back to the foundational question of can HLS or designs generated using HLS undermine security? So let's look at a threat of reverse engineering. Here, an attacker tries to identify the device technology used in an IC, identify the functionality in the IC, or the design itself. Reverse engineering is typically a precursor to Trojan insertion and piracy attacks. Anyone in the downstream of an IC design flow can do reverse engineering. For example, the SoC integration house can try to reverse engineer the third-party IP. The foundry could be a reverse engineering actor, or the end user can reverse engineer the products that they buy on the market. Typically, the reverse engineering at an IC level takes an integrated circuit, depackages it, delayers it, images those individual layers, and annotates them, and analyzes the images and extracts the design. There used to be a company called Chipworks. I think it was been taken over. I don't know who took it over, that performs reverse engineering. So let us consider the reverse engineering attack on HLS created designs. The attacker obtains the IC or IP from a third party, from an IP vendor or a foundry, and the reverse engineers for example, the layout, obtains the design specifications, for example, the clock frequencies, the I/O ports, and so on, from the data sheets of the IP. But we assume that they do not know the controller. If you remember when I showed you the HLS, there was the data path and the controller. We assume that it is hardened using logic locking and other techniques. Their objective is to recover, as an attacker, the controller, or even better, the original C code. Their attack plan is somehow to use the heuristics used by HLS to generate these designs. So let me rephrase the attack as follows. Consider this super CDFG, as I call it. Here, each vertex is an operator in each clock cycle. Each edge is a possible data flow between the vertices. The attacker starts with this super CDFG and prunes away all infeasible CDFGs out of this super CDFG. And hopefully, what remains are, or ideally is, a single CDFG that is implemented by the controller that we showed you on this slide. Right here is the controller. So we don't know that. He does so, or they do so, by using the heuristics of HLS to reduce the number of plausible CDFGs. The question is, how many CDFGs can be implemented by the design? So ideally, as I mentioned, the heuristic-based pruning should recover the original CDFG shown at the bottom here, out of the from the super CDFG at the top. For that, we'll use a variety of constraints, 3 key sets of constraints. The Datapath constraints involve investigating the register transfer level blocks and interconnections between them. Like, for example, answering the question, which blocks write to which registers by looking at the multiplexer points. For example, either multiplier 5 or add 2 writes to register R5. If you go to controller constraints, some of the heuristics are as follows. Identify select signals. signals that connect the controller with all the multiplexers that sit before the registers and the operators. Identify relationships between select signals and state signals. For example, in states 3, in states 4 and 5, add 2 writes to register R5. In state 2, for example, the multiplier 5 might write to the register R5. But we know that only one state is active at any time because each state is associated with a clock cycle as an artifact of high-level synthesis. So that is either state 2 or 3 or 4 or 5 can be active at any time, and so on. So the next thing you want to do is the input-output constraints. The IP, for example, the input arrives, say, at cycle 0. So the operator connected to it should compute, for example, should compute in the next cycle. For example, the IP, the input X that may arrive at cycle 0 is stored in register R1. I don't know if you can see these things here. Similarly, when is the output ready? It could be ready in some cycle X. If so, an operator connected to it should write to the registers, output registers in the previous cycle. There's also the latency consideration. Some operators take 1 cycle, some operators like multipliers take 2 cycles. So if you combine and put all of these constraints and impose these constraints, apply these constraints as part of your reverse engineering step, you could potentially recover the original CDFG. So here I have a table where we have some HLS benchmarks. The number of CDFGs without any of these prunings are shown in the next column right here. Then you apply the constraints iteratively. And at the end, if you look at the rightmost column, you'll see the pruned away CDFGs. At the end, you started with a large number, for example, for AES, 2 to the large number CDFGs, to about 512 equivalent CDFGs that are functionally equivalent and oftentimes structurally equivalent as well. If you look at the BQF, again, you start with 2 to the 53 possible CDFGs and come to prune them down to 2 to the 2 or 4 equivalent CDFGs by applying all of these constraints. These are from here to here, you apply data path constraints. From here to here, you apply the data path plus controller constraints. And the last step is to also bring in the IO constraints. So we applied this attack on commercial and open source high-level synthesis tools. We call them A, B, C, D, and E. We don't name them. We formulated all these constraints as SAT formulas and used a SAT solver to derive these CDFGs. We checked the recovered CDFGs to make sure that they're functionally and structurally equivalent. We checked that all the CDFGs, in terms of functional equivalence, we call it's the IO equivalence, input-output equivalence. In terms of structural equivalence, we also look at results at the intermediate points. We call them the compare points, that these intermediate results are also equivalent. So this is one way. This is an attack on designs that are generated using high-level synthesis by applying or repurposing the heuristics used by them. Let me see. So yeah, so the question is, will obfuscation help in protecting the IP? So I think I'll be getting there in a second or so. Thank you, Dr. Ananda Mohan. Just looking at this. So the next threat, we have, what time did we have, how much more time do I have? I can usually go through the slides or skip the slides and continue on the discussion. Any suggestions on how much time I have? Okay. So let's look at third-party IP and malicious third-party IP. Here, instead of talking about an attack, I'll talk about a defense. The threat model we consider is one of rogue 3P IP vendors. This could subsume bugs in these 3P IPs. Of course, one has to trust someone. We trust the SOC integrator in this context. And the SOC integrator has control only over the integration, but not over the internal details of the IP. And we assume, for simplicity, Trojans that can cause wrong outputs. Furthermore, if the 3P IP modules are sourced from the same vendor, we assume that they can collude. These are what I call distributed Trojans to make it slightly interesting. Okay, so this is a classic high-level synthesis example. On the left-hand side, that's the high-level code. On the right-hand side, you have the CDFG. This is a simple specification and a simple CDFG. The modules here are sourced from IP vendors. We don't know if they are trustworthy. We assume that they are untrustworthy. The objective is then to generate an RTL for a trustworthy system that can detect or mute the effects of Trojans in the sourced IPs. So one straightforward approach is duplication. And this is what we do for detecting natural faults. You make it copies and make sure that the original and the duplicate do not share hardware. The classical assumption here is at most one module is faulty. The approach is straightforward. What you do, you duplicate, you map the duplicate copies to run on disjoint hardware. Checkers detect output mismatch. Key assumption, at most one module is faulty. Now let's come to malicious 3P IPs. The third-party IP vendor sells Trojan-infected, potentially infected, or even buggy 3P IP modules. Integrator synthesizes SOC using these IP modules. And anytime you instantiate an IP, it's replicated every time that happens. Right? So if you look at this, if you duplicate a module, if it is infected from the same vendor, then even if it is a distinct module, it has the same Trojan. Components with Trojans produce same malicious outputs. That's the other thing. So checkers cannot detect malicious outputs because this violates the assumption for reliability. Right? So reliability does not imply security. I hope that. So besides just replication, Trojans may collude, as I pointed out. There are at least two types of collusions. Parent-child, where both of them are from the same vendor and they could potentially collude, or parent-to-parent collusions, where if the module's from the same vendor, then they could potentially collude as well. So, for example, to prevent parent-to-parent collusion, you should make sure that at least one of the parent operations, for example, this one, O1, operates on a module from a different vendor so as to break the dependency. So a quick summary here is it's not just about duplication. You want to do diversification of vendors. If you want to, for example, if you want to prevent, for this example, parent-to-parent collusion, you need at least 3 vendors. And the colors give you the vendors. So this can be done during high-level synthesis, after scheduling, during mapping. Of course, the overhead is the number of multipliers now increases to 5, and the number of adders remains 4. So the cost, it's not just about duplication and so on. You need to procure these multiple IPs from multiple sources. As Dr. Ananda Mohan pointed out, you can also do high-level synthesis for obfuscation. This is a different way of, IP theft is a different way of looking at reverse engineering. The threat model is one of, as I said, IP theft. Obfuscation is the proposed defense. Obfuscated design typically goes through the untrusted phases of the IC design flow, all in the obfuscated form. And after production, once the chips come back, the correct keys can be applied and activated. There are different kinds of obfuscations. And to keep it at a high level synthesis for obfuscation looks something like this. And this is, as you can agree, is quite intuitive. There are control flows, there are constants, operations, and dependencies between operations in a design. So each of those four ways, each of them present four ways to obfuscate an algorithm. For example, obfuscate operations. It's easy to apply. Reasonable area overhead, pick the dummy operations that are already available. Each operation type you pick a predefined set of alternatives, and so on. So you can do obfuscate operations. But something even more intuitive is obfuscation of constants, where you have coefficients. For example, in your filters, you remove them from the circuit. Instead of synthesizing them, you store them in registers. This suddenly offers dramatically more protection. It results in, of course, less logic level optimizations and increased area overhead. So in contrast, logic level and netlist level operations operate on optimized logic synthesis. In some sense, some of these things are already baked in if you don't do obfuscation at the high level. So this is roughly the obfuscation flow. Take a design and do obfuscation during high-level synthesis. You get an obfuscated RTL, then you do synthesis, go through the backend flow, you get an obfuscated netlist. The problem here is now you have to integrate the obfuscations into an HLS. So there's another way of doing it where you get the RTL from the various HLS tools here, for example, Mentor, Xilinx, Intel, BlueSpec, or Cadence, and apply obfuscations at the RTL. This is still before the netlist and gate level, so they still have some of this semantic information, high-level semantic information. For example, you can still do constant obfuscation, and you can still do control obfuscation. So on that note, what I'll do is I'll pause here, stop here, and conclude. As I said, these are the takeaways I highlighted initially, and I want to reiterate those takeaways or conclusions. On one hand, high level is a promising level to design security accelerators. It is a promising level to design and security. HLS can be used for Trojan detection and isolation. I showed you one approach. HLS can be used to watermark designs. If you just Google, you'll find a few papers. HLS can be used for meaningful design obfuscation. We started looking into that. We have a few papers. One of the tools that we have developed is called Assure. Again, you can Google that. HLS can be used for seamless and meaningful taint propagation, complementing the software level taint propagation. However, you got to be careful and mindful of the drawbacks that are associated with HLS. HLS generated designs can be reverse engineered. A black hat or an attacker can use HLS to undermine designs, to weaken crypto, to drain battery, and so on and so forth. On that note, thank you, and time permitting, I can take questions, and thanks for your patience.
Thank you, sir. Thank you for the wonderful presentation, and thank you for taking your precious time out. I know that you are traveling, but despite your tight schedules, you are consented to be part of our conference program. Thanks a lot, sir. So I would like to open it to the audience for question answers. Okay, there is a question here. Mike.
Hi, Ramesh. Can you hear me? Yeah. What about this Trojan insertion? How do we analyze or how do we check it out during the fabrication level? Is there any process we can undergo so that at the fabric, even giving the net list to the companies, so without the knowledge of the even concern, it has been inserted. And moreover, the logic cannot be changed when we check the algorithms also. So moreover, it doesn't have a big impact in the gate level, netlist level. So how do we analyze that?
Professor Ramesh Karri, we are not able to hear you. You are muted.
I'm not muted. I think maybe you muted me somewhere. I could.
No. Okay.
Yeah, it's
fine.
okay. Now
okay.
it's clear. Yeah.
Okay, good. So just want to repeat. I think the area of hardware security is still emerging. At least I would like to think so. So most questions that come out of these presentations are usually questions for research. So the question here is, you have an IP that has Trojans, and you did not catch those Trojans. They were deeply embedded. And then how do you catch that during fabrication?
Yeah.
So security verification at every step, post RTL, post gate level, post netlist level, and even during the, so you got to do verification at every step. And each step, hopefully it is a different party that does the verification. So hopefully they catch it. But this is the problem with just like is problem with Trojans, whether be it in software or in hardware. There is no guarantee that the resulting chip has no bugs or no Trojans. The only thing you could do, and this is what typically you do, this is the difference between test and trust. In test, all you have to do is make sure that the chip does the expected thing, right? You can do verification and you can guarantee that it does the right, it matches the specification. In security or in trust, you want to make sure that not only does it do the expected thing, it doesn't do anything else. And that opens up a huge problem space that is beyond the scope of a typical VLSI test community or a verification community or a validation community, and is an open problem. I hope I answered your question.
Yeah. That's the reason chip manufacturer and device manufacturer should have a test and a trust.
Yeah.
Thank you.
Yeah, hi Ramesh. So I wanted to ask you, what about putting a wrapper about the chip so that it only gives me the function what I want? For example, if it is a time bomb, if I make the clock of hardware go reduce rather than increase, there will be no time bomb.
Mm-hmm. Yeah. So for every, I don't know, I mean, I'm from.
Every thief can be caught. So that is the
I know.
notion
So
in
I'm trying to. Yes. So my take on this is a slightly different take. So I'm from Andhra. So my mom says uh, for every daridram there is satakoti daridraliki anantakoti upayalu is what they say. For every fix, there are many ways of going around the fix. That's for those of you, many of you understand Telugu, I guess, or. So the answer is yes, you can have wrappers. In fact, there's lots of, even in testing, you do security wrappers and so on. At some point, you want to make sure that the wrappers themselves are not buggy, right? So there are other approaches, not even running it slow, but you can also reset the clock. That's another approach to defending against these time bombs, right? You can periodically reset the clock, reset the state, and the time bomb dissipates or goes away. But for whatever is useful for the defender can also be repurposed or used by the attacker. As computations happen in the field, you can use these capabilities of resetting computations for suddenly resetting some sensitive computations. So that's similarly for test, was used typically to identify bugs, and JTAG attacks and scan attacks that we showed a long time ago were essentially repurposing those beneficial capabilities. So that's my answer. Again, although you can have wrappers, you still have to verify them. You got to be and make sure that those wrappers do not have use cases where an attacker can benefit from them. And usually there are use cases. Does that make sense?
Yeah, it makes sense in a sense, there is no provable operating system and there is no
Exactly.
provable secure hardware.
Yeah. So in that sense, there is a guaranteed job. So security is never going away in some sense, whether it is software or hardware or the system level thing.
These are all undecidable problems from a theoretician.
Yep. And we had this discussion the last time I visited you at IIT Bombay.
Okay. So any more questions?
If not, thank you so much for having me.